Determining the empirical formula of a compound. First of all, the empirical formula is a type of molecular formula that gives you the simplest whole number ratio of the elements in a compound. So you will see it with an example. So you have a molecular formula which is very useful because it will tell you the specific elements that you have in a compound and how many atoms of each element you have in the compound. Now, the empirical formula is a simplification of your molecular formula. I have here, for example, cyclohexane. The molecular formula for cyclohexane contains 6 carbons and 12 hydrogens. Now, the empirical formula, as you have in your definition, is the simplest whole number ratio. So 6 and 12, you can simplify those two numbers divided by 6. If you divide 6 by 6, you will get 1, which is what I have here. If you divide 12 by 6, you will get your number 2, which is the subscripts that I have for the hydrogen in that formula. We cannot simplify the 1 and the 2 any further. So C1H2 is the empirical formula for cyclohexane. So the empirical formula is telling you, in this case, for every carbon that you have in cyclohexane, there are 2 hydrogen atoms. So that's the information that the empirical formula is giving you. Now, there are compounds that the molecular formula and the empirical formula are exactly the same. For example, water. Water, the formula is H2O. So you have 2 hydrogens, 1 oxygen, and 2 and 1, they cannot be simplified any further. So percent composition, which is something that you're going to be calculating as part of your report, it's like telling you if you have a specific amount of a compound, and let's say that compound is cyclohexane. Out of that specific amount of cyclohexane, what percent is carbon? What percentage is hydrogen? So that's what the percent composition is telling you. It will be specific for a specific element in your compound. So I have the formula here, and I will show you with an example. You have the mass of the element in the formula, or the mass of the element that you actually want to find out the percent composition, divided by the molar mass times 100. So you have your definition for molar mass, but I will show you like how to actually calculate the molar mass. So I have down here molar mass, and what I have is a representation of what you have in the periodic table for hydrogen and carbon. So you have your number, your atomic number, which is 1 for hydrogen and 6 for carbon. And then you have 1.008. That number represents the molar mass for hydrogen. And then for carbon, we have 12.01. So your formula for cyclohexane, C6H12. So the molar mass is actually the sum of all the molar masses of every single element that you have in a compound. So for cyclohexane, we have 6 carbons, 12 hydrogens. And you have down here the math to find out the molar mass for cyclohexane. So my subscript 6, it's telling me how many carbons there are in the formula. So I have 6 times every carbon has a mass of 12.01 grams per mole, plus you have hydrogen, the second element in your compound. 12 hydrogens, so I have my subscript comes here. The mass for every hydrogen is 1.008 grams per mole. So when you solve the part for carbon, and you will see why I'm solving both separately. When you do 6 times 12.01, that will give you this 72.06 grams per mole. When you do 12 times 1.008, that's how you get 12.095 grams per mole. So the first term here corresponds to the amount for carbon, and the second term is for your hydrogen. So when you add everything together, you will get 84.16 grams per mole. So that number is the molar mass for cyclohexane. So now that you have the molar mass, we can calculate the percent composition. So I'm going to find out the percent composition for carbon in cyclohexane. So you solve your mathematical operation here. In the previous problem, we have 6 atoms of carbon in cyclohexane. The mass of each one is 12.01 grams per mole. So that's going to give you 72.06 grams per mole. So if we're calculating the percent composition for carbon, that's the amount out of your total 84.16 grams per mole for cyclohexane. 72.06 are carbon. So that number, if we're finding the percent composition, that 72.06 corresponds to the mass of the element in the formula, because we're trying to find out the percent composition for carbon. The molar mass is the total mass for the compound, so we have the part that corresponds to carbon over the total, which is the molar mass for the whole compound. So now you just need to do your 72.06 divided by the total 84.16 times 100, and we have 85.6% carbon. So out of your 84.16 grams per mole, 72.06 grams per mole are carbon, which means that that amount represents an 85.6% out of the total. So you can calculate the percent composition for hydrogen doing the same thing, or the total percentage will be 100. So if you have only 2 elements in your compound, carbon and hydrogen, and for carbon you have 85.6%, 100 minus your 85.6% is going to give you the percentage for your second element, which is the hydrogen. But just to practice again with the equation, I'm showing you the calculation here. So this part we already solved when we were calculating the molar mass. So that's why I did them separately, so I didn't have to do the math again. So you have 12 hydrogen atoms in your cyclohexane. Each one has a mass of 1.008 grams per mole. So that's giving you 12.096 grams per mole. So the percent composition for hydrogen will be the mass that's coming from the hydrogen, your 12.096 grams per mole, divided by the total, which is the molar mass for cyclohexane, C6H12. And you get 14.4%. If you have any amount of cyclohexane, I'm writing down here 20 grams. Okay? If you have 20 grams of cyclohexane, in your 20 grams, 85.6% corresponds to carbon and 14.4% corresponds to hydrogen. Any amount, you can have 1 gram. In 1 gram, out of your 1 gram, 85.6% will be carbon, 14.4% will be hydrogen. Those proportions are always the same for cyclohexane, regardless of what amount of cyclohexane you have. So this type of calculation you need to know as part of your pre-lab questions. So the molar mass is actually a conversion factor. You know that anything that you have represented as an equality, you can use to write down two possible conversion factors. For every equality, you can get two possible conversion factors. So molar mass, you have units of grams and units of moles. So you can use the molar mass to convert any amount given in moles to a new amount in grams. Or you can convert any amount given in grams to moles. Those two units are related by the molar mass, so you can use the molar mass to convert one of those units to the other. So I'm still using the same example, my cyclohexane. We calculated the molar mass, adding everything together, 84.16 grams per mole. So that molar mass means that every mole of cyclohexane C6H12 has a mass equal to 84.16 grams. So if you have 84.16 grams of C6H12, the amount that you have that is equivalent to that amount in grams will be 1 mole. So your equality converted to fractions that we can use as conversion factors are given here. I have 1 mole over 84.16, or the other one, 84.16 grams over 1 mole. So if 84.16 grams is equivalent to 1 mole, we can use that to find out how many moles you have if instead of having 84.16 grams, you have 25 grams of C6H12. So I'm setting up my calculation. Look, the given amount is your 25.0 grams of C6H12. So that's my given amount that I'm writing right here. To convert that amount to the number of moles that you need to calculate, you're using your conversion factor. Out of your two options, 1 mole over 84.16 or 84.16 over 1 mole, you have to choose the one that has the unit that you're trying to get on the top part. Your given amount is in grams, 25 grams. The amount that you're trying to calculate, it's in moles. So you need to use the conversion factor that I have on the left side, because in that one you have unit of mole on top of your conversion factor. So I have my problem, 25 grams of C6H12 times 1 mole of C6H12 divided by 84.16 grams of C6H12. Your units, your grams, are canceling out with grams. So when you solve your problem, the only unit that is not canceling out is moles, which is the unit that you're actually trying to calculate. And that's the amount of moles that you have. So what that number represents, look, when you have 84.16 grams of C6H12, what you have is 1 mole. Now, you don't have 84.16 grams. The given amount is 25. 25 is a smaller number than 84.16. So you should expect before doing your calculation to get a number that is smaller than 1. For you to have 1 mole, you need 84.16 grams. Now, if you have only 25 grams, the number of moles that you actually have is this 0.297, smaller than 1. So that's a number that actually makes sense. So converting any amount in grams to moles, what you actually are doing is dividing by the molar mass. So when you divide by the molar mass, units for molar mass are grams over moles. So if you're dividing your grams, any amount in grams divided by the molar mass, which is grams over mole, look at what's happening. Division is the same as multiplication of the reciprocal. So your grams are here, and then this molar mass, grams over mole, multiplication of your reciprocal will look like this, which is the same that you have in that calculation. That's why I'm going to write down here, to go from grams to moles, you have to divide by the molar mass. And you can do the same with any compound. As long as you know the molar mass of the compound and you're given an amount in grams, you can convert your grams to moles, dividing your grams by the molar mass. The opposite, it's also true. If you're given an amount in moles, and I'm starting here in moles, and you need to find out grams going in that direction, you have to multiply your number of moles times the molar mass. So I have here an example which is going to be similar to what you have to do in the experiment for your calculations. So you have a sample that it's 5 grams in total. Out of your 5 grams, 1.3 grams are phosphorus, and you have 3.87 grams of chlorine. And you're trying to find out your empirical formula, okay? So your compound contains phosphorus and chlorine, P and Cl. So what you're trying to find out is that subscript that you have for P and for Cl. Those numbers are going to tell you like how many P's or how many P atoms you have, how many Cl's you have in your empirical formula. So let's start the calculation. So when you're trying to solve this problem, the first thing that you have to do is convert your grams to moles. And I already showed you that if you want to convert grams to moles, you have to divide by the molar mass. So we have P and we have Cl. So I'm going to do this individually. Okay, so I have 1.13 and I have 3.87 for Cl. Okay. Now you need to look at the periodic table. The molar mass of P and the molar mass of Cl you have to find using the periodic table. The 1.008 that I use for hydrogen in your cyclohexane, I copy that number from the periodic table. The 12.01 that I use for carbon, I copy that number from the periodic table. So you can check your lab manual and the periodic table that you have in your lab manual. For P, you have 30.97. So I have that every mole for P has a mass equal to 30.97 grams. So you can calculate the number of moles. That's going to be 1.13 times 1 divided by 30.97. 0.0365. You can cancel your grams. So we have here number of moles of P. So now we're doing the same thing for Cl. And looking at the periodic table from your book, 35.45 grams. 3.87 times 1 divided by 35.45. That's 0.109. So I have my number of moles for P and for Cl. Now the second step, and the second thing that you have to do is that you need to divide your both number of moles by the smallest one. So I'm going to do this. Look, you have here in your problem that your formula is going to be PCl. So I'm going to write down my number of moles for P, 0.0365. For Cl, you have 0.19. So you need to divide both number of moles by the smallest number of moles. The smallest one is this 0.0365. So this here is going to give you 1, and then your Cl, when you do 0.109 divided by 0.0365, that's going to give you 2.99. 2.99, it's a number that you can actually round to 3. When you have your formulas, empirical formula, molecular formula, you have whole numbers. So you cannot write down this as a 2.99. 2.99 is an actual number that you can round to 3. You have an example in your lab manual where the number is not close enough to a whole number for you to round. In those cases, you have to multiply your formula by a factor until you get a whole number or something that is close enough to a whole number that you can round it. So this right here is the empirical formula for this compound containing phosphorus and chlorine. So the procedure for your experiment, and I'm going to go over this very quickly. You're going to clean the crucible. You're going to be using an intense flame for everything. So cleaning your crucible for 2 minutes, you know the precautions that you have to take while working with your crucibles. You're not touching them with your hands, not with paper towel. You're always using the tongs to move the crucible from one place to another, always. So you're cleaning the crucible for 2 minutes, and in this experiment we're using the crucible and the lid. So you have to clean both. After your 2 minutes, you're going to remove the crucible from the flame. You're going to set up your crucible on top of your wire screen or your wire gauze. Put the crucible on top of your wire screen, put the lid with it, and wait until it cools down at room temperature. Once your crucible is at room temperature, take the crucible with you to the mass balance in the book so you can write down the number. So you're going to determine the mass of your crucible, and remember to copy all of the numbers that you have in the mass balance. Write down the number for the mass in your book, and now you need a piece of magnesium. I will show you how to coil the piece of magnesium. It needs to be like a specific or in a specific range in size, so it will go all the way to the bottom of your crucible. So you will coil your magnesium, and with the crucible still on the mass balance, don't remove it. With the crucible still on the mass balance, you're going to put the piece of magnesium inside of your crucible. So now you're going to copy the new mass. You have the mass of your empty crucible, and now you have the mass of the crucible with the piece of magnesium. And you need to put the lid too. I forgot. Yeah. You need the empty crucible with the lid. I'm sorry. Everything will be with the lid for this experiment. So empty crucible with the lid. Put the magnesium in, and now put the lid again and copy the mass for the crucible with the magnesium and the lid. Now you're going back to your station, turn on the Bunsen burner, set up the intense flame, and you're going to start heating up your magnesium. So magnesium is going to react with air. So the lid in your setup, it needs to be on but tilted because air needs to get in. So you will be able to see when the reaction starts. So I will be walking around to make sure that your flame is close enough to the crucible and that it's hot enough. If your flame is not close enough or is not hot enough, your reaction will take a lot of time to start. So I will check that everything is working properly. So once you see your magnesium glowing, you will be able to see the light coming from the magnesium. At that point, your reaction is starting. If you see formation of smoke coming out of your crucible, use the tongs and put the lid on the crucible. That smoke is your actual product. So if the lid is open and the smoke escapes, it means that the mass of your product is going to be different or less than the amount that you're supposed to have. So whenever you see the smoke coming out of your crucible, use the tongs and put the lid, like close the crucible entirely. So you're going to continue heating, and actually I have here 5 minutes, but the amount of time is going to depend on how long it takes for your piece of magnesium to burn entirely. So at those 5 minutes, like you're not removing the crucible or anything. After 5 minutes, when you see your magnesium glowing, like time it 5 minutes, carefully use the tongs, open the lid, okay? Open the lid and see if the magnesium is still glowing. If it's still glowing, cover the crucible with the lid again and just wait another 5 minutes. So keep waiting. 5 more minutes, open the lid and look at your magnesium. So you're not turning off the Bunsen burner, you're not removing the crucible from the flame, okay? You're just checking if the reaction is over. Once you open the crucible, you remove the lid and you check if there's no more light coming off from the magnesium. You can think the reaction is over, but we're going to check anyways. You're going to take a glass rod and carefully you're going to tap your solid inside the crucible. Sometimes the magnesium will crumble and you don't have to even poke it, but sometimes it will burn, but it will remain with the same shape of your coil like when you started the experiment with. So just poke it with your glass rod to see if the magnesium actually crumbles. It will look like a powder. If that happens, now you're good. You can keep going on. So you're going to leave it there for another 5 minutes. After you check that the magnesium crumbles, you keep another 5 minutes. After those 5 minutes, now you're going to turn off the Bunsen burner for the first time. Everything that you have done so far is the crucible on the Bunsen burner since the beginning. So now you're going to turn off the Bunsen burner for the first time and you're going to wait for your crucible to cool down. And you have to wait for the crucible to cool down. You need to add water. The crucible is super hot and your product is super hot. If you add 1 or 2 drops of water and your product is still hot, it will splatter out of your crucible and you're losing your product. The crucible can break if you decrease the temperature too quickly. So you're going to wait until the crucible cools down and then you're going to add 10 drops of distilled water. When you're adding the water, you're actually converting a byproduct to your final product. You have this as part of the discussion. Your magnesium reacts first with nitrogen from air to form magnesium nitride. When you add the water, which is what you're doing here in your step number 7, your magnesium nitride is converted to magnesium hydroxide and ammonium. And now you keep heating and your magnesium hydroxide goes to the actual product, which is magnesium oxide. So you're adding the water and now you're going to heat up your product again. You're heating up your product to evaporate the water that you have in your crucible now. So you're going to let the lid open because you're evaporating the water and the water needs to escape from the crucible. Intense flame for 5 minutes. Turn off the crucible. Turn off the Bunsen burner and let your crucible cool down. Now in this step number 9, after your crucible cools down, this is the first time that you're going to the mass balance after your steps 1 and 2, like 2 and 3, where you were determining the mass of your empty crucible and the mass of your crucible with the magnesium. Let the crucible cool down. Use your tongs and use the wire gauze to move your crucible from your station all the way to the mass balance, and remember to use the same one. You use a mass balance for your empty crucible, the same one for your crucible with the magnesium, and you're going to use the same one to weigh your crucible with your product. So this number 9 will give you the mass of your crucible with the lid and the product after the first heating. Okay. All of this that you have been doing is the first one. After you have that number, now you're going to come back to your station and you're going to reheat for another 5 minutes. Cool it down to room temperature and take it with you to the mass balance and determine the mass again. The mass that you're getting for your first weighing and the second one, they should be close to each other. So whenever you're determining those two masses, show me the numbers before you start the second sample. After you're done with the first sample, you're going to repeat everything with your second sample. So you're doing again, cleaning the crucible and the lid with an intense flame for 2 minutes, determining the mass of the crucible with the lid, then with the magnesium, everything again. Once you're done, waste container will be in the fume hood, so put your solid waste in the waste container. Clean your crucible with a damp paper towel. Return everything to the original location. Even though this looks like super long, it is not. Sometimes the first 5 minutes it's enough for your magnesium to be converted to your product entirely. Sometimes it takes a little bit longer, but hopefully everything will go well and we will finish in no time.